Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. In the previous lecture, we learnt about the four phases in which we are going to divide the lecture series. The first phase is going to be the innovative architecture behind DeepSeek. So that's phase number one right over here. Phase number two is the training methodology itself, the rise of reinforcement learning, and how they relied on RL to teach complex reasoning to the model using rule based reward systems. That's phase number two. Phase number three is GPU optimization tricks. So, how they used NVIDIA's parallel thread execution PTX over CUDA, let's say. And phase number four is their model ecosystem itself. So, they did not stop at just building a huge 671 billion parameter model, but that large model was essentially distilled down into a much smaller model whose size was around 1.5 billion parameters. So that's essentially phase number four. We are going to go through phase number one to phase number two, phase number three, and phase number four. And in this lecture, today we are going to start with phase number one, which is essentially the innovative architecture behind DeepSeek and what makes it so efficient. The two major aspects of their architecture which contribute to the DeepSeek efficiency is essentially something called multi-head latent attention MLA, which makes the attention mechanism itself more efficient. And second is the mixture of experts, which means that although the number of parameters is 671 billion, all of those parameters are not active at the same time. Only about 37 billion parameters are. So essentially, parts of the parameters are turned off and parts are turned on, like light bulbs going on and off. And that makes the model extremely efficient in its computations. Parameters which are not needed are turned off. When they are needed, they are suddenly turned on and then they start working. Right? Then we have multi token prediction, quantization, and rotary positional encodings as well, which we are going to learn about. So the first thing which I want to teach you is multi-head latent attention. And then I was thinking about how to exactly teach this concept, right? Because the concept itself is pretty advanced. So if you search about multi-head if you search about multi-head latent attention, you'll get certain blog posts which talk about this. So they do talk about essentially what multi-head attention is. And if you scroll down here below, you'll see that it's just one page of this blog article, and they start out with multi-query attention, grouped query attention, and they go to rotary positional encoding. And then there is a very small section on multi-head latent attention, which is impossible for a person to understand if they are just starting out to explore what DeepSeek is. And so I don't want to follow that approach of just going through a simple lecture and explaining MLA by assuming that you know the prerequisite knowledge. Instead, as I mentioned to you at the start of the series itself, I want to make this lecture series very deep. So the way I'm going to explain multi-head latent attention is through a four-part process. First, we are going to understand the architecture of LLMs itself, and that's going to be the main purpose of today's lecture. I believe that without having an intuition of the LLM architecture, it's impossible to understand latent attention. Then we are going to understand why there was a need for self attention and what is the self attention mechanism itself. Once we understand self attention, we are going to understand how self attention was transformed into multi head attention and what does it mean to have multiple attention heads. That's the third aspect over here. And then the fourth aspect is essentially key value cache. So then we are going to understand, okay, multi head attention works and it really works very well. But then what can we start doing to improve the efficiency of multi head attention, to make it computationally faster, to make sure that the number of parameters which we are storing in the memory is reduced? And that's when key value cache comes into the picture. Only when you truly understand key value cache, then you will slowly start to understand multi-head latent attention. So after KV cache, then we are going to understand MLA. But I'm going to devote a lot of time to develop your foundations in these first four concepts before we go ahead to MLA itself. Many of these blog posts which I mentioned right now, they assume that you're already familiar with this. So in the Build DeepSeek from Scratch series, we had 43 lectures explaining you everything about these different aspects. In this lecture series, I'm not going to go as deep. So for example, today I'm going to have just one lecture on the LLM architecture, but in the Build LLM from Scratch, there were 3 to 4 lectures, right? So my aim is that I want to explain this knowledge to you, but also I want to make sure that beginners who have started watching this series, they also feel connected with the series. So the challenge for me was to come up with a new set of lecture notes specifically for this series, because I'm trying to explain a concept in 1 hour, but also I want to make sure that I don't lose out beginners in the process. So I've made a whole series of new notes for explaining these different concepts. All right, so I hope everyone has understood the flow of how we are going to understand multi-head latent attention. Today, our main aim is to understand the architecture of LLMs. So, after today's lecture, all of you should have a mental map or a visual roadmap of what happens with a word or a token when it goes into an LLM. First of all, let me explain what does it mean architecture of an LLM, right? So, if you pass in some certain a sentence or a sequence of words, we have seen that when a sequence of words is passed into an LLM, what the LLM essentially does is that it predicts the next word or it predicts the next token rather. So an LLM or a large language model can be thought of as the next token prediction engine, right? So it can be thought of as the next token prediction engine. And just like an engine, so let's say if I go and search engine car, and if I copy this right now, copy image, or let me copy a good image right now. If I copy this image right now, And if I paste it over here, right, this is an engine. So if we are calling it the next token prediction engine, we need to know how does this engine actually work? How does this engine actually work? In the previous lecture, we have learned some things about the engine. What have we learned? The first thing which we have learned about this engine is that it has a huge number of parameters. So, to give you an example, GPT-3 has around 175 billion parameters, whereas GPT-4, although it's not been released yet, they probably have around a trillion parameters. GPT 4.5, which was just released 2 to 3 days back, maybe have 5 trillion or 10 trillion parameters. That's not yet released. But we know that this engine has a huge number of parameters which are acting together. And if you search engine car working, right, you'll see that there is this piston cylinder mechanism here, right? And the piston cylinder mechanism essentially works, and then that's how the engine operates. Similarly, we need to make sure that we understand how do these parameters actually work? Where are these parameters? Can we open the engine of the large language model and try to see what happens inside that engine? Essentially, given a sequence of words. So, similarly to a car, right? When a fuel is injected into this engine, what essentially happens with that fuel and how is that converted into the motion of the car? Similarly, when a sequence of words is passed to this engine, what's underneath the LLM which causes us to predict the next word? So think of the sequence of words as a fuel, and think of the LLM, of course, as the engine, and the next word as the motion of the car, let's say. So here we want to open the engine, right? And to truly understand how the engine actually works, we need to understand the architecture of the engine, which means that we need to understand what are the different components inside that engine, how these components are actually connected to each other, then what exactly happens with the fuel or the sequence of words when it is being passed through this architecture. That's what we essentially want to understand in today's lecture. So you can think of today's lecture as going to your car, opening the engine, and trying to peek inside the engine and trying to really understand how do you work. One way to also think about this is that all of us have worked with Chat GPT now, right? And if we ask something like, give me an essay, give me a short essay on friendship, right? And we see that GPT essentially predicts one token at a time. How does this actually work? What's the architecture which is giving me this one token at a time prediction? That's what we are going to find out today. Okay, I'm going to try to keep this lecture as beginner friendly as possible. So you'll see that there's a whole story which I've constructed to explain how the LLM architecture works. I don't think this has ever been done before. So it's also a bit of an experiment for me to explain this to you in a story kind of a format. But I hope through this explanation you will understand really how the LLM architecture is working. Okay, so here's the schematic of what happens when you take a look at the engine, what happens when you open the black box, what lies within the black box itself. And when you open the black box, you will see that there are a huge number of things which pop out. It's not simple at all. If you think of the 175 billion parameters, the 175 billion parameters are scattered across multiple places of this black box. In other words, the LLM architecture is quite complex. Um, and why do you think it might be complex? Well, because in making the next token prediction, the LLM is actually learning language itself, right? I strongly think that language learning is a byproduct of the next token prediction task. And to learn the language, you cannot have an engine which is small, or you cannot have an engine which is not complex enough. So that's why our engine is quite complex. We have a huge number of blocks or layers which are linked together. Today we are going to try to understand this architecture. So if you just take a look at this schematic, you'll see that broadly this schematic is divided into three parts. There is this part number one over here, part number one. Then there is a part number two, which I've marked by saying that it's something which is called as the transformer block, which let me mark like this. And then there is the part number three, which is basically the part which is the output part. So here's where the next token is actually predicted. So the architecture of the LLM can be thought of in three parts. The first part can be thought of as the input. The second part can be thought of as the processor. And the third part essentially can be thought of as the output, right? In the input part, we have the sentence. Let's say if you have the sentence, any sentence, let's say the next day is bright. There are a number of things which happen with that sentence, and with every token or every word in that sentence before we pass it to the processor. And the things which happen to the sentence are, first of all, we do something which is called as tokenization. Secondly, we do token embedding, and third, we do something called as positional embedding. After these three steps are done, the input is essentially passed to the processor, which is also called as transformer block. Within the transformer block, there are six different things: the normalization layer, multi-head attention layer, dropout, second normalization layer, feed forward neural network, another layer of dropout. These two plus signs here are what are called as skip connections or shortcut connections. Finally, when we come out of the processor or the transformer block, we have the output. And here we have another layer, normalization layer, and the final layer for the next token prediction. Okay, so all of what I said right now, if you are learning this for the first time, you might be thinking, what is going on here? And all of this seems too complex. Let's break it down further. And that's exactly what I'm going to do right now. But keep close eye or attention on this part which I've marked as purple. Because the first innovation which I'm going to explain later, which is the multi-head latent attention or MLA here, is to do with this aspect, which is titled as multi-head attention. So, out of the entire architecture, there are two major places where DeepSeek has contributed in making their innovations. The first is this called as multi-head attention, that block, and the second is the feed-forward neural network. So, let me actually rub this a bit right now. So the MLA or the multi-head attention is an innovation which happened in this part of the architecture. So I'm going to call this MLA, and the mixture of experts innovation that actually happened in this part of the architecture, MOE. So again, if you don't understand the architecture itself, you will not be able to appreciate where the innovation has happened. But it's like, imagine opening an engine, right? And you have opened the DeepSeek engine right now. And the DeepSeek engine is that of a car which has performed very well, and you want to understand why has it performed very well. You open the engine, you see all these parts, and now I'm telling you there are two parts in this engine which were augmented to improve the performance. But all right, coming back to the engine itself, how do the input, processor, and the output actually work? And now my challenge for this lecture was that I wanted to create one lecture in which I explain all of this to you. I explain the input, I explain the processor, and I explain the output. And I wanted to explain it in an easy to understand manner so that you get an intuitive feel for the architecture itself. So the way I thought of doing this was that I thought from the perspective of the fuel. So if you're a fuel, let's say, and if you go to the car engine, what happens with you? Do you go to the engine first, then are you rotated because of the pistons, and then some kind of a power or energy is produced? If I understand the life of the fuel, I'll effectively understand how the engine works, right? Similarly, today I want to show you the life cycle of a single word and what happens to a single word when it essentially goes through the LLM architecture. Think about it this way, right? When we put this sentence, give me a short essay on friendship, or let's say if we are going to complete the next sentence, and The sentence which I'm going to take is, let's say, the next day is bright. The next day is bright. It goes into the LLM engine, and then the next token is predicted. Let's say the next token is and, the next day is bright and. What I want to show you is we are going to focus on just one token, and we are going to see what happens to this token as it goes through every single step of this LLM architecture. And by looking at from the perspective of the token, so I want you to now imagine that you are that token. You are that token, and I will now take you through what happens to the token as it goes through several of these layers in the LLM architecture itself, and ultimately we predict the next token. So that's how I'm going to explain this whole lecture to you in a story format. I'm going to explain this lecture to you as if you are the token now. Imagine you are the token. You are surrounded by a bunch of words, and suddenly you are thrown to the LLM architecture. Let's understand the life cycle of a single token. So that's how the next part of this lecture is going to be. All right, so let's embark on this journey together, in which we will understand how the life of a token essentially looks like. So the title which I have given to this section is the journey of a token through the LLM architecture. So what I first did is I went to Chat GPT and I asked it to write a short paragraph on friends, right? So I took some random sentence from this, which is a true friend accepts you. Let's say we are looking at this sentence. A true friend accepts you, which is a sequence of 5 words. Let's say that's my input sequence at the moment, and we have to predict the next token given this input sequence. And I'm going to specifically focus on the word friend, and I'm going to think from the perspective of friend. Now, put yourself in the shoes of this word or this token. First of all, this token. So I'm going to interchangeably use token and word, although they are not the same. For the sake of simplicity, I'm just going to say one token is equal to one word. So put yourself in the shoes of this token now. What do you see? You see that there are these other tokens around me, right? There is a, true, accepts, you. There are these four other tokens which I'm used to hang out with, just like friends hang out together. I'm used to having these as my neighbors and my friends. A, true, accepts, and you. These are the four neighbors of this token which we have chosen, that is friend. Now, suddenly, what happens in the first step is that the first step in the LLM architecture is that that's the step of isolation. So, currently, we are looking at this phase, right, which is the input phase, right? The first step which happens in the input phase is the isolation phase. So, what happens is that the word is detached from its neighbors. The word is isolated from its neighbors. So imagine like a group of friends, and every person is isolated from their neighbors. So this word is isolated, and we look at it in isolation. That's phase number one. Phase number two is essentially called as token ID assignment, which means that imagine now every word is isolated and we want to put a badge or a stamp on every word or every token. Similar to how, let's say, if you are getting enrolled in a camp or enrolled in military or any other group activity, you are given ID, that's your roll number. Or in school, all of us have roll numbers, right? It's similar to that. So every token is isolated and then it's assigned a separate token ID. The way the token ID is assigned, it's, I'm calling it getting your badge. The way the token ID is assigned is a very interesting process. We have a book of token IDs. So you can think of this like a encyclopedia or a book of token IDs. In this book, basically all the possible tokens are listed. All the possible tokens or all the possible words. And then there is a number which is associated with every word. In this book, there are not just words, there can be characters or there can be even subwords. So this book consists of characters like A, B up to Z. It even consists of subwords such as maybe CR can be a word in this vocabulary. Then it may consist of subwords like ization, that can be a subword. And then it also consists of words like, let's say, token can be a full word in this vocabulary, enter can be a full word in this vocabulary, begin can be a full word in this vocabulary. So you can think of this book of token IDs as consisting of characters, words, and subwords. So let me write this down here. That's going to be very important. This book of token IDs essentially consists of characters, it consists of words, and it also consists of subwords. So as a result, essentially we make sure that every token or every word which is isolated, it finds certain badge. There is no token or no word which is isolated which won't find any badge. Readers who are familiar with the concept of byte pair encoding, remember that to create this book of token ID itself, there is a certain scheme which is called as a byte pair encoding scheme. This is a subword tokenization scheme. And to create this book of token ID, we use this scheme. So GPT-2, for example, relied on the byte pair encoding mechanism to create its vocabulary. This vocabulary is this book of token IDs is also called as a vocabulary, and then it changes from one large language model to another. So let's say GPT-2 has a vocabulary of 50,000. GPT-4 might have a vocabulary which is higher, maybe 100,000, right? So based on the LLM which we are using, the token ID which is assigned to, let's say, this friend might change. So I am using a large language model here right now, which has a vocabulary size of 50,000, which means that there are 50,000 tokens, which might be a combination of characters, words, and subwords. All right. Then what I'm going to do is that I am going to essentially look at this vocabulary and I'm going to find where the friend comes into the picture, and I'm going to find the token ID associated with it, right? So for the word friend, the token ID which is associated now is 2012. So I'm going to note that down. So that's the badge, or that's the roll number which is now assigned to this token. So the roll number assigned to the token friend is now 2012. Similarly, all the other tokens or all the other words will get a similar badge. That's the first step, or rather, that's phase number two, which is token ID assignment. So now imagine that this token friend, which was isolated from its neighbors, it has now been given a badge or a stamp which is 2012. That's phase number two. I did not go into the details of how this book of token ID was created, because if you want more details on this, there is a separate lecture on creating this vocabulary itself for every large language model, and it's called byte pair encoding from scratch. It's present in the lecture series Build LLM from Scratch. But for now, stay with me. Imagine you are this token friend, you have been isolated, and now you have been given a badge or you have been given a roll number. Then you essentially come to phase number three. In phase number three, something interesting essentially happens. In phase number three, the you until now you just had one number associated with you, right? But now you are going to have a huge vector of numbers which are going to be associated with you. And this is called as token embedding assignment. One way to think of this is that, let's say we have an entrance examination which has 768 questions, and each question essentially tests a certain feature of you. So now we are looking at the word friend, right? Each question will test, are you a noun, are you a gender, are you a verb, are you a sport, are you an emotion, etc. We actually don't know what these features or what these questions are, but I'm just trying to explain to you so that you get an intuition of what token embedding is. So imagine there are 768 questions like this which are asked to every token which we have isolated, and then based on the answers we get to understand something about that token, whether it's a noun, whether it's a sport, whether it's a adjective, whether it's something which appears always at the end of a sentence, whether it's something related to gender, whether it's something related to monarchy like kings, princes, queens, etc. So here we are actually getting to know about the meaning of the token itself. In the token id assignment we did not get to know anything about the meaning, but in phase 3 in token embedding, because we ask a big list of questions, we get to know something about the meaning. And based on the answers which are given, there is a result. So every token, so now this friend, right, it will have some values for each of these questions. Maybe the values are point 0.1, point 0.2, point 0.1, point 0.3, etc. And if we are assuming that there are 768 questions, this will now be a vector of 768 values. One thing which I want to point out here is that this number of questions here, 768, that vary from one large language model to another large language model. So now if you go and see, let's see for GPT-2. GPT-2 token embedding dimension. So if we search GPT-2 token embedding dimension, we'll see that it's 768, right? But here also GPT-2 small had 768, but the largest GPT-2 had 1600 dimensions. So this number of questions 768 actually varies from one large language model to another. So here what we are going to do is that we are going to assume that the number of questions is 768 for GPT-2. But remember that if the token goes to different LLMs, it might be asked different questions. So now imagine you are a token, you have been given a badge or a roll number, and suddenly you are asked this huge set of 768 questions. You respond, then your answers are collected in one 768 dimensional vector. That is called as the token embedding vector. So now along with the badge, you also carry your result with you. So you have a badge with you and you have this result of 768 values with you. That's what has happened to you until this stage, right? That's the stage of token embedding. The difference again between token ID is that token ID does not carry any notion about semantics, whereas token embedding assignment, we care a lot about the meaning of the word itself. The reason token embedding is done is that to create LLMs, you ultimately need to extract meaning, right? You're teaching something about the language to the model. So this is a very crucial step. These set of questions or these uh, set of features which are collected about every single token. So until now, every token has a badge and every token has 768 value result sheet which they take along with them. Then one more thing which also matters is your position among your neighbors. So here if you see, a true friend accepts you. So friend comes in the middle of the sentence, right? It comes at position number 3 over here. So a comes at position number 1, true comes at position 2, friend comes at position number 3, accepts comes at position number 4, and you comes at position number 5. So the friend is coming at position number 3, and that position also matters. Why does the position matter? Because if you say the dog chased another dog. Okay, if you take a look at this sentence, you need to somehow be aware that this dog is basically different than this second dog. So if you just take the meanings of the words, right, as in phase number 3, we just took the meanings. So the token embedding for this dog and this dog will be the same. But actually there are two separate dogs and we need to teach the model related to that. So the only way to distinguish between this dog and this dog is to know that this comes at position number 2 and this comes at position number 5. So as a result, it's important to also have some knowledge about the position. So similar to the 768 questions which we asked, 768 questions will again be asked with respect to the position. So remember that although this number varies across different models, if you fix a particular language model, the number of questions which are asked in token embedding and the number of questions which are asked in the positional embeddings are the same. So if we are looking at GPT-2 small right now as the model, there were 768 questions asked in token embedding. Similarly, 768 questions will be asked in positional embedding. And what might these positions or what might these questions be? They might be something like, are you at the beginning, or are you around the middle of the sequence, or do you encode long range dependencies, etc. Actually no one knows what these questions might be, but I thought this the simplest way to explain about positional embeddings and token embeddings. So now in phase number 3, every token had a token embedding which is associated with them. That's a 768 dimensional vector. And when you come to phase number 4, based on the position you are asked these 768 questions, right? So you will also have a 768 dimensional position embedding which is associated with you. So now imagine what all a token is subjected to. A token first has a stamp or a badge of token ID. Then it has the token embedding result. Those are the questions which it needs to answer. That's the first test. Then the token goes to another test, which is positional embedding. And then it again has these 768 values. It's a lot of processing which needs to be done for every token. It essentially has to go through a huge number of tests. And then in step number 5, what we do is that we add the result of your token embeddings plus the positional embeddings. So you don't have to carry these two results separately anymore. You merge both of them. So the token embedding, which is now 768 dimensional vector, and the position embedding, which is now a 768 dimensional vector, is added together. And that is what is called as input embedding. So this is the input embedding for the token which is friend. That's a 768 dimensional vector. We'll have similar input embeddings for all the other tokens or all the other words, but here I am showing to you the input embedding for the token which is friend. That's the result of the token embedding plus the positional embedding. So now you don't have to carry these two results separately, you just carry one result. That's now the 768 dimensional vector which is associated with you as a token. That is the most important distinguishing factor you carry with you in the rest of the journey now. Think of the journey, right? You are first isolated, you are given the badge, you are given the first test of token embedding, second test of token embedding. Finally, after going through all of these steps, you now have one thing to distinguish you, and that's the input embedding. So you can think of this as your uniform. Now this is a uniform which is specially created for you, and you wear that uniform as a token. Every friend or every token along with you, every other word along with you will wear a separate uniform. Why will they wear a separate uniform? Because their meanings would be different. So they would answer these questions differently. Their positions would be different. So they would answer these questions separately. So the uniform for every token will be different. And until this stage, what we have done until now, these 5 steps which we saw, are essentially what is happening in the input block or the input layer. So that's the first part which we have studied until now. And now I think these 3 steps which have been mentioned here will be very easy for you to understand. The first is the tokenization, the second is the token embedding, the third is the positional embedding. That's exactly what we saw, right? And then the token embedding and the positional embedding are added together to give something which is called as the input embedding. That's all which happens. And remember the tokenized text. Here we saw the token ID assignment through the vocabulary or through the book of token IDs. So that's the input embedding. After every token goes through the input block, which is phase part number 1 over here, they have a uniform which distinguishes them from the other tokens. All right. So that's the first part, which is the input. Then once you have an uniform, only then you are ready to go to the next part, which is the processor. So as a token, you have a uniform now, and now you're ready to onboard the train to the transformer block. So it's similar to Harry Potter, let's say, where you can go to the school only if you have, let's say, a certain uniform, you belong to a certain house, let's say Gryffindor or Ravenclaw, Slytherin, etc. So every word or every token now has a uniform, and now you're finally ready to onboard the train to the transformer block. So here you see these 5 will be sitting together in the transformer block. A true friend accepts you. And whenever I show uniform right now, you should think that the uniform means a 768 dimensional vector. Every token now, so for the transformer block, it does not understand words. It does not even understand the meanings of words. All it essentially knows is that every token is a 768 dimensional vector. Some magical things will happen in the transformer block so that the meanings between different tokens will be understood very clearly, and the model itself will learn about the language. So the transformer block essentially is where all the magic happens. The second processor part is where really everything is happening. This part over here, this processor part is really where all the magic happens. And how, so you might be thinking that how do LLMs work so well? They almost interact with me as a human. Although they predict the next token, they seem to have learned something about language itself. They summarize tasks, they are good at grammar checking, they draft emails for me, they do complex coding for me. All that is because of what is happening in the transformer block. So now every token essentially goes on a journey through to the transformer block itself. Okay, now to think of the transformer block, we need to understand that the transformer block is like a train with a huge number of different components, right? So first we are going to look at the components of the transformer block train itself. And I'm not going to go through all the components in detail. I'm just going to briefly explain to you what each component of the transformer block does. So now imagine that these five passengers have been assigned a compartment, right? And all of them are now input embedding 768 dimensions. They have to go through 1, 2, 3, 4, 5, 6 steps within one transformer block. What are these 6 steps? So you can think, if you think of a transformer block as a train, these 6 steps can be thought of as 6 compartments which are connected together. So once you join the train, you have to go with your neighbors and you have to go through all these 6 steps. The first step is essentially layer normalization, which means that these 768 dimensional vectors. So let me now just focus on friend. This 768 dimensional vector for friend is normalized, which means its mean and standard deviation are adjusted. So that mean becomes 0 and standard deviation becomes 1. That step is easy. Then we come to multi-head attention. So here you see I have marked this with a different color because this is truly the innovation which powers the transformer block. In multi-head attention, we essentially learn, if we look at one token, how much attention should be given to other tokens. So if you look at friend, how much attention should be given to true, accepts, and you. So multi-head attention essentially encodes something about the context. If you look at one token, you suddenly make a map of how important are all the other tokens. And if you think about it, that helps a lot in understanding things about the language, in understanding context of a sentence itself, or understanding context of a paragraph. So if I say something like, I am from Pune, India, I speak. So here, if you have to complete the next sentence, you need to know that you need to pay more attention to Pune and India because that is where I am from, right? So you need and not pay too much attention to the first three tokens, maybe. So that is why attention mechanism is important to understand the context of a sentence and to predict the next token. We are going to learn about the attention mechanism in a lot more detail in the next lecture. But remember that that's the second compartment of the transformer block. The third compartment of the transformer block is the dropout layer. If you have learnt about neural networks, dropout is essentially if there are 100 parameters and dropout factor is zero point 0.5, you randomly turn 50 of them 0. Why? Because what if some parameters are lazy and they are not learning anything at all? Suddenly, if the other parameters are now dropped out, which means they are set to 0, these parameters have no option but to learn something on their own. So dropout is a mechanism to get lazy parameters back into action. It improves the generalization performance and it prevents overfitting. So there are two layers of dropout. If you see, there is one layer of dropout here, and then there is one layer of dropout again. After the dropout layer, we have a skip connection or a shortcut connection. Shortcut connections just help the gradient to flow through an alternate path, and they make sure that we don't have the vanishing gradient problem. Then, so after we go through normalization, then multi-head attention, dropout. After that, we have another normalization layer which does the same function as the first one. Then we have a feed forward neural network. This is again a very important component of the transformer block itself. This feed forward neural network, if you think about it, so there are 768 dimensions, right, in friend, which is my token right now. The feed forward neural network essentially takes it into a much higher dimensional space, which is 4 times 768, and then it compresses it back into a 768 dimensional space. So this expansion contraction makes sure that we are exploring more richer spaces. We are exploring spaces which have more dimensions and more parameters. So that just makes sure that our language models have enough parameters to capture additional complexity. This feed forward neural network is where the mixture of experts innovation has actually happened for DeepSeek. Finally, we have another dropout layer, and then we have another skip connection or a shortcut connection. Remember these plus signs, wherever they are there, they resemble skip or shortcut connections, and they just make sure that the gradient has alternative routes to flow. Because if the gradient flows in a chained manner, and if the one gradient is small, once it's multiplied together, the gradient will become zero, right? Or if the gradient is large and if it's multiplied together, it will blow up. So it can lead to vanishing gradient problem where the learning will stop, or it can lead to the exploding gradient problem where the learning will be very unstable. So this is how these five tokens have to go through these different steps. Every token has to go through normalization, multi-head attention, dropout, skip, connection, normalization, again feed forward neural network, again dropout layer again, and then one more skip connection. So that's the transformer block. And if you see this schematic which we saw at the beginning of the lecture, you will see that the same thing has been mentioned over here. Every token has to go through a layer normalization, attention, dropout, then skip connection, again a layer normalization, a feed forward neural network, dropout, and a skip connection. So that's the journey which has to be followed through a token. This seems like such a tedious journey to follow, right? I have, first of all, I have to go through all these five steps to get my uniform. And then on top of that, after that, I have to go through every block, every transformer block, and go through these steps. But there is one more additional layer of complexity, that just like this one transformer block, one large language model has multiple transformer blocks, right? So if I say GPT-2, how many transformer blocks does GPT-2 have? So if you take a look at GPT-2 itself, GPT-2 small has 12 transformer blocks, GPT-2 medium has 24, GPT-2 large has 36 transformer blocks, and GPT-2 XL has 48 transformer blocks. So even if we look at the small one right now, each transformer block has all of these steps. So now every token has to essentially do all of these steps 12 times. So that's why these, if you think of one transformer block as one part of the train, there are 12 such transformer blocks which are linked together. And one token has to essentially go through all of these 12 transformer blocks. So the journey is extremely more tedious. So here I have mapped it out, right? These are 12 transformer blocks which essentially every token has to go through. So the token friend here, right? It has to go through the first transformer block, it has to go through the second, it has to go through the third. Similarly, it has to go through all of these 12 transformer blocks. So number 12 over here, there is a very tedious train journey which every token has to essentially follow. Getting a uniform is a struggle, we have to go through 5 steps. Going through the processor is an even more struggle because you have to go through all of these 12 steps again. So this is what is actually happening in the processor, which is the part number 2, which we have just seen. In the processor, what happens is that, so here I have shown one transformer block, right? You can think of this multiplied by 12 if we are using GPT small. If we are using the largest GPT-2, then it's 48 transformer blocks, and modern GPTs might have 96 or even more transformer blocks. So every token has to now go through all of these. And remember that the dimensions of a token are usually maintained even when it comes out of the transformer. So let's say the input, right? The input uniform which we saw was 768 dimensions here. If you remember, it was a 768 dimensional vector, right? Here 768. After going through all of these transformer blocks, after going through the 12 transformer blocks, it comes out of these 12 transformer blocks by retaining its dimensions. So it still has 768 dimensions. So now a true friend accepts you have come out of the transformer block, and all of them still have 768 dimensions. Naturally the values have been changed, right? And then they go through. Now we go to the output layer. There is one step of normalization here. So if you see over here, there is one step of normalization here which is called as the final layer normalization. So that step of normalization is mentioned over here. So every 768 dimensional vector again goes through this stage of normalization. And then we have one last layer which is very important. So remember, now that we have reached the last layer, we have uh, a true, so this is a true friend needs you, and each of these is a 768 dimensional vector, right? Now we have to somehow convert this 768 dimensions into our vocabulary size, which is 50,000, because now we have to predict the next token. So then every token is essentially passed through a neural network whose size is 50,000, or whose size is 768 multiplied by 50,000. So that when these vectors are multiplied with this, we result into 50,000 dimensional vectors for each token. So now the size for each token is that a true friend needs you, right? The size for each token now is going to be 50,000 after it passes through the output layer. This layer is also called as the output projection layer. And after every token goes through the output projection layer, it has a dimension equal to the vocabulary size. So remember, our vocabulary size is equal to 50,000. So this 50,000 is coming from the vocabulary size, and I'm just going to explain why do we need its dimensions to be equal to the vocabulary size. And the final last step is choosing the next token, right? So now, once we have reached the last step, what do we have? We have five tokens. A true friend accepts you, and for each of these, we have a 50,000 dimensional vector. Now what we are going to do is that we are going to look at these 50,000 dimensions. We are going to look at that index which has the highest value or the highest probability. Then we are going to find that index over here, and then we are going to look for its corresponding token. That's it. So if the index here is, so for the first uh, so a true friend accepts you, right? There are multiple input output tasks here. When a is the input, true should be the output. When a true is the input, friend should be the output. When a true friend is the input, accept should be the output. When a true friend accepts is the input, you is the output. When a true friend accepts you is the input, something else will be the output, which is for. So a true friend accepts you. If you look at this sentence and you have to predict the next token, it's not just one next token prediction tasks. There are multiple input output tasks within this same sentence. What are these input output prediction tasks? When A is the input, true should be the output, etc. And only the final thing here is relevant for us, which is the next token prediction. Initially, we'll of course not get good tokens, right? But we'll have the loss function which is based on the actual values. So this is the actual next token which I want, but the predicted ones initially will be completely far off. And that's when back propagation comes into the picture, when all the parameters which are there, they are actually optimized. We'll come to that in a moment, but for now, just let me explain the final step again. We have every token, and now every token is associated with a different uniform, let's say, whose dimensions are 50,000. Why do we have dimensions 50,000? Because we have to predict the next token for every word which is over here. So for A, we have to predict the next token. So we look at that index which has the highest, or that token ID which has the highest probability here. We go to the book of the words or book of token IDs, and then we reverse map the word which is corresponding to that token ID. So if this token ID here is, let's say, 555, or this token ID is 5000, I go to the word here which is 5000, and I ideally want true over here, but initially when things are not trained, maybe I have for. So the actual prediction might be for. Similarly, I'll get the actual predictions for true. Maybe the highest token ID is here, friend here, and then I'll get the highest token ID here, and that's how I'll predict the next token for each of these, and then I'll find the loss term between the actual value and the predicted value. That's how the entire architecture of the LLM is structured. So now if you go to the output layer, which is my final layer, here you see we have two things which are chained to each other, right? We have the final layer, normalization layer, which is connected to the output layer. And then we have the matrix for next token prediction. This logits matrix is this one which I showed to you right now. And we use that to make the next token prediction. So now you might be thinking that what are all the parameters which are optimized here? So right from the start itself, these token embedding values which are there, we do not know them a priori. So let me mark the parameters which are trained by a star. These we do not know a priori. So these are trained. Positional embedding assignment we do not know a priori. So these are trained. Then every single aspect of the transformer block has some parameters. Multi-head attention has parameters that is trained. The feed forward neural network has parameters that is trained, and there are 12 or 24 such blocks that even increases the parameter size further. So there are a huge number of parameters throughout this entire process which are trained. Even this final neural network, it has these many parameters which need to be trained. All these parameters add up together to lead to the total number of parameters, which are 175 billion or maybe a trillion. So think about the engine which we started out, right? We started out with knowing that we started out with thinking, okay, this is the LLM engine, but how does the LLM engine actually work? What are the parameters beneath the LLM engine, and where are these 175 parameters actually going? 175 billion. So now we have taken a look at the detailed architecture, which is the input, which is the processor, and which is the output. So, and we have seen the journey of a single token, right? A token essentially first goes through the input phase, which it is isolated. It is assigned a token ID or a badge. Then it's given one quiz or one set of 768 questions. That's the token embedding. It encodes meaning. Then it's given a second set of questions, which is positional embedding, that encodes its positional value. We add the token and the positional embedding, that gives the input embedding or the uniform for every token. With this uniform, different tokens sit on the train to the transformer block. And each transformer block essentially has the normalization layer, multi-head attention, dropout, normalization again, feed forward and dropout, interspersed with two skip connections. And there are 12 such blocks like this in GPT-2. In GPT-2 XL, there are, I think, 48 such blocks, but in the advanced GPTs, there might be 96 or even more number of blocks like this. So every token needs to go through all of these blocks. When it comes out of all these blocks, its size still remains 768. Then it goes through one more normalization layer, size is still 768. And then finally, we have an output layer where for every token which we have, it's converted into a vector now with size of 50,000, which is equal to the vocabulary size. And then we look at every token, basically it's 50,000 dimensional vector, and then we look at that token ID, which is the highest probability, and we use that to predict the next token. So in one sequence which we have multiple input output prediction tasks. So if we have a sequence with 5 tokens, there are 5 input output prediction tasks which essentially give our loss function. And then our loss function is basically back propagated and all the parameters are optimized. All these 175 billion parameters which come through in several stages. In token embedding, there are parameters. In positional embedding, there are parameters. Then in several aspects of the transformer block, there are parameters. In the output layer, there are parameters. All of these parameters are essentially optimized through back propagation. And then ultimately what we have is a model which has intuition about language itself, and it can also predict the next token. So next token prediction is the task. As you see here, we are predicting the next token and we are comparing with the actual value. That's the task. But in this task, since we have so many parameters, the byproduct is learning the language itself. So in today's lecture, my main purpose was to take you through the journey of a token. Think from the point of view of what happens with one token. Try to open this engine. Try to open this engine of the LLM and really try to see how the engine is actually working. And I hope I have conveyed that to you. The reason I constructed this analogy or a story of a journey of a token is for you to really understand what goes on inside the LLM architecture, because without understanding that, we cannot move ahead to the next part, which is attention. Now, the plan is that in the next lecture, I'm going to motivate why we need attention in the first place. Then we are going to look at self attention. Then we are going to look at multi head attention. Then we'll look at key value cache. So, if you see, the next plan is the need for an attention mechanism. Then we have self attention. And then ultimately, we have the multi head attention mechanism. So, all the future lectures are planned in a lot of detail. As I mentioned, this won't be a small series with 5 or 10-minute videos. Every single video of this series will be pretty long, around 40 to 45 minutes, and I will plan to go through the entire steps. So, multi head latent attention is a very important concept, but I want all of us to be at the same page when we actually understand that concept. Thanks a lot, everyone, and I really look forward to seeing you in the next lecture. Please make notes along with me. This series can get a bit difficult. I'm trying to distill the concepts in as easy to understand a manner as possible, but still there might be some challenges across the way. So please make notes so that you strengthen your concepts. Thank you, everyone, and I look forward to seeing you in the next lecture.